Let me just check one more. Okay, hello everyone. Welcome to week 6 of ISDA IoT Symposium. And apologize for a bit delay from our side. Today we have a very special speaker this evening, and it is Professor Andrew from Federation University, Australia. His research is in health informatics, in data mining in health, alternative medicine, informatics, telemedicines, and intelligence decision support systems. He's the author of over 150 peer-reviewed journal and conference articles, and 2 books as well. He's also a co-founder of a company named Spin Out, which is a kind of a remote, doing remote vital signs monitoring in Indian hospitals. Please join me to welcome Professor Andrew for his talk on IoT, real-time IoT analytics challenges. And thank you. And I am passing this on to Andrew.
Thank you very much, Satan. Am I audible? Can you hear me okay?
Yes, it is good, yeah.
Okay, very good. Look, first of all, my great apologies. Satan was very kind, but I'm late because of my fault, and I thought we were starting at 6 o'clock, not 5 o'clock. So please accept my apologies, and thank you very much for waiting. Now, do we finish at 6 o'clock?
So we have, yes, almost we need to leave 10 minutes for QA. Okay. But you are welcome, just, probably 55, and then we can have 5 or 10 minutes for the QA. Thank you.
No problem. No problem. Thank you very much. Now, I presume you can see the slides okay?
Yeah, if you make it full screen, that would be, yeah.
Okay.
That would be great.
Now, if I make it full screen like this, does it put the slides on the right page? That's okay?
Yeah, that's good.
Excellent. Well, thank you very much for the invitation, and again, please accept my apologies. What I want to talk about is some real-time Internet of Things challenges, and it's my perspective on these challenges. The way I want to talk about it is by talking about some conventional data analytics, data mining, and then some stream mining or real-time IoT analytics, and to see how some of the challenges are different. And what I'll use is an example of some algorithms that I had worked with and developed and worked with some years ago, and to illustrate some of the concepts. So first of all, let's talk about sort of some more conventional machine learning. Yeah? Now, many of the examples I talk about come from machine learning in law, because that was my background is in modelling how judges and lawyers reason, and developing machine learning models of judges' reasoning. So initially in the mid-70s, mid-90s rather, where there was a lot of effort in a lot of research in modelling how judges and reason in using logic. You know, if you look at statutes, it looks like logical clauses. The question was, could neural networks that were recently emerging in machine learning then, could neural networks be used to learn how judges reason? So how do we do that? Well, we say that the machine learning program, the neural network, is presented facts or variables from multiple cases over and over again until it learns to produce the same outcome in those cases as a judge did. Okay? After it's learned, then you can present the machine learning model with a new case, and you get a output as a judgment which is similar to the judgment that a judge made. Now, one of the key things in this approach is that you have to have all of the training cases in one large database, and you repeatedly show the machine learning algorithm all of those cases over and over again until it learns. Fayed, Osama Fayed, was one of the leading figures in machine learning in the early days, and he identified the phases that are now taken for granted. And the phases look like this in conventional data mining, that you start with some raw data, and you typically can't use all of the data. You have to select some of the data. So again, let me just say with the examples that I knew, is I started with all of the cases with family law, this is divorce law in Australia. But I couldn't use all of them. I had to select which ones I wanted to use. After you make that selection, that's called the target data, is now the selection. That's not ready to use. You have to pre-process that. Now, the pre-processing involves cleaning the data. Usually raw data has missing values. So you usually have to do something with the missing values. Usually the raw data has noise, and this is where the data has been recorded incorrectly. An example of a noise in my data is where a judge may have written that the husband was 200 years old. Okay? So that's obviously a mistake and it needs to be corrected, but sometimes it's not easy to know how to correct it. Okay? Now, I'll speak in a minute how selection and pre-processing is different in stream mining and presents great challenges. The next one is transformation. Now, transformation is where you transform the model either in different ways. Now, one of the ways is you just change the domain of the variable. So instead of it being a number, it may be categorical. So you have categorical values instead of numerical values. But as I'll show in a minute, the transformation that can sometimes be much bigger than that. Okay? And again, presents challenges for real-time analytics or stream mining. Then you can do data mining, and then you can interpret or evaluate the result. And then at the end of all of that, you can say that you have inferred new knowledge. Okay? So that's the conventional data mining steps. Many of you may have seen this diagram many times. So if we turn now to say, well, what is stream mining? Well, it's similar process. Okay? However, the data is different in that each item in the data has a timestamp. So the data arrives to the machine learning algorithm in sequence, one after another. This sequence is potentially infinite. And we want to build a model as the data comes in. We don't want to wait until all of the data is in one database and then repeatedly apply the data to the machine learning algorithm. What we want is to be able to start building the model as soon as the data arrives and then discard the data. We don't need it anymore. Okay? Why? Is because a lot of the data sets in IoT become very, very large quickly, too large to store and repeatedly exposed to a machine learning algorithm. So, for example, this is an ECG, a recording of the electrical activity around the heart in millivolts. So you can imagine there is a point arrives 1,000 times every second. So an ECG with a sampling rate of 1,000 per second means that the data value in millivolts, either positive or negative, arrives every millisecond, 1,000 times per second. And if you plot that, it looks like what you might recognize as an ECG. However, if you say, well, every time a data point arrives in millivolts, it maybe occupies 2 bytes. Okay? But you've got 1,000 of them per second, by 60 per minute, by 60 per hour, by 24 per day. That's 170 megabytes per day from that one person. So you can imagine if you're streaming the ECG from tens of thousands of people, you've got enormous data sets arriving, and that's just ECG, one variable. So if you've got the same thing from many variables, from many wearable sensors, as well as environmental sensors like the weather, the temperature in the room that the person is in, you can imagine that the attempt at trying to store all of that data in one database and then to apply it thousands and thousands of times for a machine learning algorithm becomes intractable. So what we want is to see if we can develop stream mining algorithms, machine learning algorithms that will learn something from the data as it arrives one by one. Massively Online Analytics, MOA, is an initiative from the same people who developed Weka. It's the University of Waikato in New Zealand that have developed a stream mining toolkit and environment similar to Weka, for those people who are familiar with Weka in the conventional data mining, but dedicated to stream mining. They've also released this the book just a couple of years ago, which they kindly make a HTML version available for free. I thoroughly recommend this book for anybody interested in this area, and also the toolkit. Now let me start with go back to here and say, let me start in the middle of this process and say the transformation phase is when you transform the problem or the variables. Okay? Now, in my conventional neural network with law, I was trying to predict what a judge would decide for a property split after divorce. So in Australia, if husband and wife can't divorce and they can't agree on who keeps the house or the property, the matter goes to court and a judge has to decide. I worked with lawyers closely to develop a model, to first of all, identify what are the relevant variables. And it took quite a while, and we identified 94 relevant variables. Okay? And there were things like, well, how old is the husband? How old is the wife? Do they have children? Who looks after the children? Is it the wife or the husband? What are the prospects for the husband to find a job in the future? What are the prospects for the wife to find a job? So all of these variables were identified with lawyers and judges as relevant. You know? Now, what you would normally do is say, well, let's collect data on all 94 variables and train a neural network. Now, one of the problems I had with doing that is that if you train a neural network by collecting the data on these 94 variables, exposing it to a neural network again and again and again and again, many cases, you need huge data sets because you've got so many variables, 94 variables. But what I did instead is transformed the problem. So instead of saying, well, these 94 variables are all input variables, I thought, no, let's look closely and let's break it down. Let's make a hierarchy of variables using expert knowledge, not machine learning. And so, for example, I come up with on the right of this slide, the thing that we're trying to predict. What is the percentage of the assets that the husband will receive? What's the percentage the wife will receive? And there were 3 variables. You can't see them because the tree is cut off, but it's the contributions that the husband and the wife has made to the marriage, how wealthy is the marriage, and what are the future needs of the husband compared to the wife. Future needs depends on his future needs and her future needs. What is his future needs? It's his personal prospects, his obligation to dependents, and his financial resources. So what is his personal prospects? Well, that depends on his age, his health, and his employment prospects. So you can see I've transformed this problem of 94 variables into a hierarchy of variables, interdependent, all flowing into each other. Okay? So that's changed the problem from one problem with 94 variables inferring one output to being able to have a tree where at each level in this tree, you have a neural network. So in here, there is a neural network that takes 3 variables, his age, his health, and his employment prospects, and infers his personal prospect. That is an input together with these other 2 to his future needs, okay? Which is an input together with her future needs to the future needs relative of the husband to the wife, and so on. So I hope you get the picture here that what I'm saying is transformation of the problem, for me, took the form of changing a large problem into many smaller neural networks. I think in the end, I had something like 30, 34, 35 separate neural networks. So the one at the end was the percentage split one. The husband is likely to be awarded 10 or 20 or 30 or 35, etc. % of the assets. There's a neural network learning that from the 3 variables that were the input variables, but each one of these was inferred by another neural network with its own input variables. Okay, now So that's transformation, and one of the things that I will say is that the transformation, number one, has not been researched very much. People just do it, but there isn't a good theory about how to do it well. When you try to do transformation on streaming data, you're almost completely in the dark. So I'll return to some of these points a bit later, but that's the sort of point I want to make on the transformation. Let's talk a little bit about pre-processing, and I'll go a little bit quicker now because I think the general point I want to make is some of the challenges are different. Now, one of the pre-processing challenges is encoding. This is often overlooked, and encoding just means how do you operationalize your variables. So for me, a percentage split is of the assets between husband and wife. Could be, that the wife receives 100% or 99.5% or 99 or 89.5%. But I didn't want to encode it like that. That would have given too many. It's a numerical, almost a continuous variable. I wanted to encode it as a categorical variable, to transform it into a categorical variable and decide that the categories were not even. Why? Because at one end, I've got 0 to 100, then 80 to 20, 70 to 30, 70, 30, 65, 35, 55, 45, 50, 50. So I wanted the categories to be more fine-grained, to differ by only 5%, near 50-50, but they could differ by 20% at the end. Then how do I, other variables like the husband's contribution, the words that the judge used were the husband contributed much more or more, the same, less, much less. I could have used the fuzzy logic to quantify, to map those linguistic variables onto a membership function and get a number, but I didn't. I thought I'll just encode that as a variable 10000 to stand for each of those 5 values. So if the husband contributed much more, that would be encoded as 1000. And again, the point I want to make is encoding, how you encode makes a big difference to your output of your machine learning. But there's very little research done on the actual impact. This is one paper to do with categorical variables and how different encoding makes a big difference. So when you're encoding for stream mining, it makes a potentially even bigger difference, and it's not researched very well. There's not a lot of research that says how should you encode the variable if it's streaming in. So this just shows what I was just explaining before. Noise is another challenge. Now, in conventional mining, when you've got all of your cases in one place, you can look at all of the data, all of the cases, and you can say, look, in one case, the way we did it, we had 3 people reading each case, and they to build the data set. There was manually built. But imagine if for those 3 people, we had one person read the case and said, oh, the judge said that the husband contributed more. Another person read the case and same case and said the husband contributed much more. But then the third person said much less. Well, now the third person actually made a mistake. If you can go back to the text the judgment, you'd see it's obviously rater C has made a mistake. Yeah? You know, other sources of mistakes, if your data is coming from a sensor, well, the sensor often fails. Yeah? Sometimes the sensor becomes low in power, and what it is accurate when it's high in power, but as it loses power, it transmits the wrong data. It measures, it senses incorrectly, or perhaps even transmits incorrectly. Okay? Now, when you've got all of the data in one data set, you can look at it all and you can deal with the noise more easily, because you can identify the noise more easily because you see all of the data. But when the data arrives one by one, you don't know if it's noisy or not so easily, you know, because you can't see all of the data to see, oh, this one's pretty obviously wrong. You know? Can two judges arrive at different judgments? You know? In law, yes. Because as long as they're not very different, because the law allows some discretion, some room for the two judges to be slightly different. Now, many data mining applications actually have some discretion, but this again is not studied very much. But when you talk about stream mining, then it's hardly studied at all. You almost like presume that the data that arrives is true and exact, you know, and that there can't be two different versions. But it's not actually so. Even in the ECG, where you say, well, the millivolt that is measured 1,000 times a second, you know, that's measured with a degree of uncertainty. If the sensor is fully powered, that degree of uncertainty might be in the 4th decimal place. But still, there's room for discretion. Now, if you say that your machine learning algorithm is trying to learn whether atrial fibrillation, whether a heart condition, an arrhythmia is present, you know, well, then you can encode that as a yes or no, you know, atrial fibrillation or no atrial fibrillation. You can encode it as a possibility, you know, highly likely, likely, not sure, unlikely, very unlikely. And you can allow some discretion. Your machine learning output may be unlikely or very unlikely, and it's okay, it doesn't matter. You know? So again, this idea of how do you set up the machine learning to allow for a little bit of that discretion and that uncertainty is not so easy in conventional data mining, and also is under researched, but it's hardly researched at all with stream mining. So let me say an example of this, and it's the outlier. And the outlier is the value that is so different from other values that you question it. You know? Imagine two cases here in the two cases had the variable, the contributions. The husband's contributed much more than the wife. The husband doesn't need as many resources in the future as the wife, and it's an average wealth marriage. And in case C, the judge gives the husband 10% of the property. And in case D, the same variable value, the judge gives it 55%. And in the third one, it's the case fed to a trained network, and the trained network gives it 35 to 40%. And your question is that discrepancy enough for you to say case D is an outlier, a mistake, an extreme one that we really should remove from the data set or change the value of it, because otherwise it's going to upset the machine learning. So in this one, you can see, well, the trained network learnt from both of these cases and output something kind of in between. Yeah? And that's okay. That's what the network does after repeated exposure to all of the cases. But if one of the cases is an outlier, you end up with the trained network learning the wrong thing. In stream mining, it's harder to detect outliers because you don't have all of the data at once. The data comes one at a time, and you don't know, what all of the data is. Similar thing with a missing value. Imagine if in one case we didn't have a value for the contributions. We know it's an important variable, but its value is missing. Now, in conventional mining, you do things like take all of the data and take the average for that variable. If it's numerical, if it's categorical, then you do other things, but to try to replace the missing value. You can even train another machine learning algorithm to infer the missing value. But sometimes it's not enough to get replace the missing value with a class with a value as the average for that variable, but you want to say is the average for that variable of all of the instances that have produced the same class or the same output variable. So there's different techniques for dealing with missing values, but again, they all rely on having access to the whole data set. And if the data arrives one by one, you discard that data, as is the aim in stream mining, it's not so easy to find an average to replace missing values. So you can say, well, I can do the average for that variable from the instances that have already arrived. And that's okay, but that's like a local average around only the ones that have already arrived. And that may be quite different to the real average if you had all of the values in the one place. So and there's different ways, as I was saying, of dealing with outliers. Another thing that gets overlooked in conventional data mining and is almost non-existent in stream mining is explanation. Now, in conventional data mining, where you've got all of the data in one place, let's say you use it to train a neural network and then expose that neural network trained to new data, then it produces an output, that you can measure is, correct. But if you ask a neural network to explain its reasoning, it's very difficult, because the inference is made by the collection of of lots of small internal weights inside the network. A whole field of research on explainable artificial intelligence now to try to generate explanations from the network. Explanations out of stream mining is even harder, because of this thing of data comes one by one. How I did explanations in my legal one is by using argument theories to say, well, an explanation is not actually derived from the inference anyway. And I used the theory of a philosopher, Stephen Toulmin, to say that if you want to explain an output like this, that the husband is likely to be awarded 10% of the assets, then you have to say, what are the input variables? He's contributed so much, he has needs, resources relative to the wife, the marriage is certainly wealthy. Then you have to say, how was that thick arrowed line inferred? And in this case, it's a neural network. But then I have to say a bit more. I have to say, something about what makes that neural network adequate. Well, it was trained with the right examples. It was trained with the appropriate learning rule, backpropagation of errors. I also need to say, well, why are these things relevant? Who cares about the wealth of the marriage? Well, there are precedent cases, the case of Lee, Steer and Brown in the Australian jurisdiction. Now, all of these components make up an explanation. And if you try to do this in stream mining, it's a bit difficult. This is you can embed this, as I did, in a decision support system, and that decision support system infers the 35% from using one of those 30 neural networks, and then presents to the user the reasoning used, how was this inferred. These are parts of the explanation. Usually in conventional data mining, the focus on evaluation is done on focusing on resampling, cross-validation, but there are other ways to evaluate that are ignored. Okay? Generally, a confusion matrix is where you relate actual to predicted is used, and from that confusion matrix you generate specificity, sensitivity, true positives, etc. Either cross-validation, holdout, other resampling methods of bootstrapping are available as well. Now, I want to jump now to show you a stream mining algorithm that is a PhD student of mine developed a few years ago, and it uses this idea. When we started from this point where we said, well, I wonder, once we have set up the neural network, if we can actually do it in a simpler way than training a neural network. And we took our inspiration from many scoring systems where the questionnaires where they ask you a bunch of questions and you get points for each question and you add up the points at the end. And to give you a score, a risk score, or of your risk of diabetes or things like that. These are used a lot in healthcare, these scoring systems, because they're so simple to use and they infer like a classifier infers. Okay? So we thought, well, we started working with lawyers and saying, well, instead of training a neural network, can you give us the score for each value of each variable? And can you give us the cutoff thresholds? So that if I answered the husband's contributed much more, that's 5. The husband needs much more, that's another 5 there. And it's a very wealthy marriage. It's a total of 11. Total of 11 will be in this category 55%. We're running out of time, are we? Okay, let me just.
Yeah, thank you.
Okay, so let me just give the essence of this, and then I'll stop because I think you'll get the picture of it. So this is Anthony Quinn, who did his PhD with me a few years ago. He's now running an art gallery in Daylesford down there. You can go and visit it. And essentially what he did is worked out that score. He called it an influence score, using conditional probabilities. And using conditional probabilities, you get a visualization like that says at this end there's no diabetes, at the other end there's diabetes. And when you use that influence scores to in conventional mining, it performs very similarly to other classic ones, support vector machines, C45. You see the results are pretty good. But it's doing it with conditional probabilities alone. You can set the threshold for sensitivity and specificity that you prefer. But most importantly, you can calculate these conditional probabilities as data comes in, one at a time. All you need to work out these conditional probabilities is the counts. So it makes it perfect for stream mining. You need to collect the count of all of the subsequences as the data arrives, and we developed an algorithm for doing that in real time. And I'll probably wind up now to say that this approach of using something very simple, conditional probability, but packaged in a different way, is an example of stream mining. There are many algorithms. Usually their simple count ones are used as baseline ones, but many of the other challenges of how to process, how to transform, how to deal with noise, how to deal with outliers, how to measure concept drift, all of these things are relatively under-researched. And I'll stop talking now. If anybody wants to pursue some of Anthony's work in stream mining, please feel free to join me, and we can take the work further into stream mining. But I'll apologise we started late, and I'm happy to spend a few minutes if we have time for questions.
Thank you, Andrew, for a very great talk on stream data mining, which is very, very important in IoT and IoT devices. And AI in IoT is very, very important topic, especially these days. Before moving to question QA, and I would like also to announce our next talk, which will be next Tuesday on AI in big data analytics for IoT, which will be, which is our speaker will be from Melbourne University, Dr. Aravinda Rao. and hope to see you all there. So thank you, Andrew, for a great talk. And any questions from Andrew? We have time for QA, and you are welcome to type your questions in QA, or just ask me to unmute, and you can just talk directly to Andrew. Okay, we have, I think, one question. I think we have the question is, what are the various expert systems where we adopt classification for knowledge acquisitions? So what are various expert systems where we adopt classification for knowledge acquisition? Yeah.
The knowledge acquisition, is the term used to where you build a knowledge, where you build a model of knowledge, and there is a number of different approaches to knowledge acquisition, and they range, if you can imagine a continuum, from at one end is totally manual, where a knowledge engineer builds a model by talking to experts, and at the other end there is almost no involvement of the knowledge of a knowledge engineer. Instead, it's then the model is built entirely from data from decisions made. So imagine that continuum, and then there are methods in each along that continuum. So the supervised methods along the machine learning end are the methods where the cases that you collect, the examples you collect, have all the variables plus the right answer. So the supervised machine learning is given the right answer. The deep learning approaches now don't need the supervision, because they can sort of figure out the patterns themselves and build a model without being explicitly told what is the right answer for each case. At the other end, there's a number of techniques that are semi-automated, and they do things like help classify or categorize cases to identify what is what are the underlying sort of concepts and stuff. Some of them come out of cognitive science. There's a whole lot out of techniques called the repertory grid techniques. So there's a whole continuum of them.
Yeah. And we have two more questions right now. One of them is, how can we relate data analytics to machine learning?
Yeah, look, in the let me answer this in the with a story from in the early days, where I had trained my first neural networks with the machine learning in law, and the term data mining was not in common use, and I had just finished a cup of coffee with my PhD supervisor, who said that suggested that I should submit a publication to a data mining conference, and I said, I'm not sure that I do data mining. I train neural networks and machine learning person. And he said, no, it's all data mining. So the words data mining and machine learning were, not not clearly defined then. It was data mining was a new term that tried to incorporate machine learning done by the AI people with statistical inferencing done by the statisticians with mathematical linear and programming and other things done by the mathematicians. Yeah. So the confluence of those three disciplines was led to this new term called data mining that tried to identify that each of these three different fields were doing similar things. They called them different things. The statisticians, didn't have a word pre-processing, but they pre-processed their data. Now, data analytics is a phrase, is a concept that tries to recognise that data mining is too narrow, and data analytics includes doing data mining on huge data sets that includes the visualization, presenting data visually, and as well as explaining. So data analytics tends to be another one of these new words emerging that tries to encompass concepts from earlier things. I try not to get too hung up about words.
Yeah, thank you, Andrew, for it also very it is confusing to the type of concepts, data mining, analytics, machine learning. You answered very well. Thank you. And another question we have: could we use Weka as a reliable data mining tool compared to Python?
I also say with let me answer this again with a kind of a story from the early days of data mining, where statisticians would not talk to data mining people because the statisticians, the techniques in, say, inferential statistics, are based on really sound theories, and they saw that the computer science people were rough and ready. As long as they wrote a program that produced the right answer, the computer scientists were happy. And the statisticians were saying, look, unless I can demonstrate and theoretically prove my algorithm, it's useless. The mathematicians were in that camp as well. Mathematicians continuously strive to prove that their algorithms will generate the correct outcome. The computer science people don't care. They just use whatever tool they can as long as it gets the right answer. And what happens is everybody gets into their favorite tools kits and tool sets and thinks that their way of doing things is better than the other. Now it's the same thing. Whether you use the off-the-shelf Weka, or whether you code up in Python, to me it doesn't matter. When do you need to use Python is when you need to implement your own thing, like we did for the Anthony's awesome program. It doesn't exist in Weka, or it doesn't work quickly enough in Weka, or Weka doesn't use the memory efficiently enough and it goes too slow in Weka. So Weka is not really, Weka is a great tool for learning and for playing around. If you need the efficiency, the scalability, go to R, go to Python, go to whatever, code up. If you can't find the algorithm in Weka, you have to go to R or Python or whatever. So it's horses for courses, and don't get hung up about,
Yep. Thank you. I think we don't any other questions, and we are running out of the time. I think we have another Noor, do we have another seminar after this one, or?
We are done, Sadar. We are done. Yeah, this is it.
Yep.
You can close the session.
There is one at 6 o'clock, is there?
No, Andrew, we do not have anything.
No. I think it is finished.
Yeah.
So,
okay. I'm very sorry. I think I saw 6 o'clock somewhere. I wrote down 6 o'clock.
Yeah.
And,
I think Wednesday talks are at 6 o'clock. Monday
yeah.
and Tuesday and Thursday we have it from 5.
Look, I'm very, very sorry. Yeah.
Yeah, thank you so much. Very great talk on stream mining, and
well, it wasn't, but thank you.
We really enjoyed. And thank you so much, all participants, for your patience, and hope to see you all next week. We have 2 more weeks for this symposium, and next talk is by Aravinda from Melbourne University, a great talk on AI in IoT, and also we have some other talks from Amazon and some other professional industry and academic professionals. Thank you so much, and see you all. Thank you.
Thank you very much. See you. Bye-bye, everybody. Thank you. Thanks for your patience.
Thank you.